Good afternoon, everybody. Welcome to this webinar. I'm very glad to see you all. My name is Sara Pittanet. I am the coordinator of the Blue Cloud 2026 project, and I'm welcoming all of you today to this second webinar of a series that we are running as part of the Blue Cloud initiative, a series of webinars dedicated to fair data principles applied to the marine domain. This is part of the Blue Cloud Training Academy, which is delivering a series of materials, webinars, and courses to introduce you all on the offer that Blue Cloud is bringing to the marine data landscape. So while we wait for a few more participants to join, I'll anticipate that this webinar is being recorded, as you'll hear, and that the materials will be available online also afterwards. So I hope that you can see and hear us very well. So let's get started. Let me first introduce you very briefly Blue Cloud. Blue Cloud is a project funded by the European Commission under the Horizon Europe program. And it was started, it dates back years ago from a pilot initiative that started in 2019. And we are running now a second follow-up phase. It's a project that is aiming at building a pilot, a cloud-based infrastructure for marine research. The main purpose of the Blue Cloud is building a federated European ecosystem, so a complex, convoluted ecosystems where to combine data sources, data sets, products, combined with computing resources, analytics resources, and experimental platforms. You'll hear about them. We call them virtual labs, with virtual laboratories, to serve a broader scope, to serve the needs of marine environment and marine knowledge agendas and different research teams working to accomplish these different missions. We are also aiming, and our entire work is aimed at supporting open science at European level, but also beyond Europe. And these services that this Blue Cloud infrastructure is delivering are also supporting the implementation of digital twins of the ocean applications. Here's the overview of the Blue Cloud offer in a nutshell. At the core of this image, you see the core services that Blue Cloud is offering. So a platform, a virtual research environment that allows for collaboration among teams, sharing of data and data products, and computing facilities and software and resources, reuse and reproducibility via fair and open science practices. On the left side of the image, you'll see all the offer that comes from the data providers that feed Blue Cloud with the data set and data products. They come from the marine and ocean environments, and they will be at the core of the webinar today, since we will soon give the floor to representatives of some of these facilities to introduce you to some of the practices that they are putting in place within this ecosystem to improve findability and interoperability of data sets and reusability across different teams. On the right side, you see the products that will come out of Blue Cloud, such as virtual laboratories, so products from collaborative research in different domains that are linked to marine science, from coastal ocean to fisheries to environmental indicators, but also a series of data workbenches, which are data flows that Blue Cloud is working to deliver as continuous real-time available products on some of the key essential ocean variable dynamics to understand and assess the ocean properties. So physical workbench, a chemical workbench, and an ecosystem workbench looking at plankton mainly. I mentioned Blue Cloud is a complete environment where users, researchers mainly, can access data set and data products, can share and collaborative work on experiments, and can perform analysis and processes via a number of facilities, services, and computing resources. We don't force approaches, but we welcome collaboration, and we offer aspects and technologies that allows you to just focus on your science by relying on other inputs. And we are sure that this environment enriches the scientific teams that work within it exactly by sharing practices and products. This is the consortium that builds up Blue Cloud. So we are 40 institutes across Europe, and the project itself is run by 3 entities. So myself, I represent the project coordination team from Trust IT, but then we have Maris, who is the technical coordinator of the project, and CNR in Italy, who acts as scientific and administrative coordination. And this is an overview of the audience that we expect today in this webinar. So you all registered from many different countries. So we are really glad to see you coming, not just from Europe, but also from outside Europe. We hope you will see yourself represented in this list. On the left, you also see some of the institutes that signed up. And we also have a pretty balanced, I would say, situation in terms of gender balance of the participants to this webinar today. Okay, while we wait for our speakers to get ready, I kindly ask you all to take any of the devices that you have with you, whether it be your PC, your laptop, your phone, and access this very, very short survey that will help us warm in a little bit the atmosphere. So, or whether you scan the QR code that you see, or you go to menti.com and type in the code that you can see there, 68754265. So while you do that, and I'll be back in a minute. So, yeah, so you can also see the code in this page. So I invite you all to join this Mentimeter survey. We want to just ask you what comes to your mind when you hear about data federation. So that's the question that we'd like to ask you. Sorry, let me just. Can you access the Menti? Then just give me a sign if you can log in. Oh yes, now I see something is moving. Great. So let me show this again. Very good. Okay. So I see interoperability, data integration. Okay. Distributed. Oh, standards. That's a nice one. Credentials. Something that was less expected. So don't be shy. Try to log in and do this. Okay. Another, also for those that haven't accessed the Menti yet. Oh, difficult. Yeah, it's this difficult. That's why we're here today. Some of our speakers will try to make your life easier by explaining what have you already done. In fact, I see best practices. In fact, you've seen in the presentation before that We have many different providers. 3 of them are in this panel, and today we'll give you some tips or tools or methods that they've applied. Okay, that's a good start. So we'll see if by the end of these 90 minutes you'll get, let's say, your expectations fully achieved. And with that, I give the floor to the first speaker for today, Tjerk Krager, who is a project engineer at Maris, acting also, as I already mentioned, as technical coordinator of Blue Cloud. And he will give you a first explanation about what we mean by federation, data federation in Blue Cloud. So Tjerk, the floor is yours.
Thanks, Sarah. Yes, so today I will give you a short summary of the Blue Cloud approach for optimized federation. And then after my presentation, we can look at the examples of the Blue data infrastructures themselves. So as Sarah already mentioned in her introduction, the Blue Cloud pilot project started in 2019 with the goal to have a platform for smart federation where we get access to multiple data repositories, tools, and computing facilities, and where we want to really show and demonstrate the potential of cloud-based open science, and also function as a marine thematic node. So that was the initial goal when we started the pilot Blue Cloud project. And then we had on the one side a virtual research environment where the users can run their analytical workflows and demonstrators. And on the other side, the more upstream service, we would have the data discovery and access service that would allow to get access to data from a set of Blue data infrastructures that we had in the consortium. And that harmonized access to the data, that's really the main point of that optimized federation that we wanted to achieve. And to do this, we had to apply common standards and interoperability solutions. So on the left, we see the Blue data infrastructures that were originally in the Blue Cloud pilot project. And on the right, we see the infrastructures that facilitate the virtual research environment, as well as the data discovery and access service. And this is also something Sarah already mentioned, but the main outcomes of the project were the access service to the data, the virtual research environment, and to showcase the functionalities and the capabilities of the virtual research environment, we set up a few virtual labs with demonstrators, for example, the plankton genomics, marine environmental indicators, to really showcase what was possible. And if you look from the user point of view at the data discovery service, you will be able to look at the data in a two-step approach. So first of all, a generic recipe to look at the metadata from these different data infrastructures. And then if you find what you are looking for, you can download the data and then push it into your virtual research environment. And from the point of view of the Blue data infrastructures, it can give some more wider outreach to potential users that might not be aware of the data infrastructure, but because of Blue Cloud, it might the users might go to that data infrastructure. And here we see some of the Blue data infrastructures and the kind of data that they offer, which is a lot. And to dive a little bit more deep into the concept of the data discovery and access service, this first step, it's really on the metadata using a common Blue Cloud metadata template that we based on the ISO 19115 metadata standard. And then secondly, depending on the Blue data infrastructure, you would be able to go to the dataset level, so to the granular level, where you would have more specific metadata that also varies over the data infrastructures. And you can imagine that because these data infrastructures are set up from they have different backgrounds. On the dataset level, the metadata can still differ quite a bit, and that's why the metadata at that level can differ. This architecture is from the data discovery service. I will not dive too deeply into this, but it basically links to components that and it showcases how much work is needed to achieve this harmonized access to the data. And if you look at this level 1 here, we see on the left, we see the the parameters, so the Blue Cloud metadata template that we used for this level 1 search, and that we use a DApp brokering service to harvest that metadata from the data infrastructures and to provide a first initial search on the general aspects that you see here, the title, the abstract, the bounding box, the temporal extent, some of the more generic concepts. And then for the level 2, where actually you are getting access to the data and the more specific metadata related to the data sets, we had to set up specific services for each Blue data infrastructure, also based on what was already there. And then we try to improve them to achieve the needs of the access service. And then now in the Blue Cloud 2026 project, we want to expand this data discovery service by expanding the functionality of the web services that are provided, by including semantic brokering as part of the interface. And we want to include additional Blue data infrastructures. And one very important aspect that came from the user point of view is that we want to have subsetting services. Because the user, they want to have targeted queries based on what kind of data they want. So, for example, a C region for a certain time period with a certain depth range, and then give back a single data file that contains all the data for that certain query, instead of having to download multiple tens or hundreds of data sets that they have to process themselves in a Jupyter notebook. So this is really to achieve more ease of use for the user and allow for easier use in the virtual research environment and work with the data. And also in the next years, we want to add URIs to the vocabularies in the metadata template and add also additional elements to the Blue Cloud metadata template that we already had. And for the BDIs individually, we want to push the so-called triples to include in the metadata based on the vocabularies for the terms, the term codes, and the vocabularies. And then we want to target for the NERC vocabulary service, which is a large vocabulary that hosts many marine parameters, so we can really achieve interoperability on the lowest level. And then finally, the current actions, I will not go into them all, but here we see on screen the data infrastructures that we will include in the data discovery service. We have the new Beacon tool, which is a powerful data lake that is now being tested by some of our partners to see if this can really help with the subsetting that I mentioned before. And the fair implementation profile we want to set up for each Blue data infrastructure, and there will be a talk about this later on the agenda. But these fair implementation profiles can really showcase on the different GoFair metrics where we can still improve or what we have already been doing well. And finally, we will deploy some federated monitoring for the components of the DDoS. So that was my short summary, and I think now then I give the floor to Katrina.
Yes, thanks a lot, Tjerk. So let's go immediately into the works, I would say. So Katrina will show how they're making Eurobis biology metadata interoperable for Blue Cloud VRAs. So Katrina Exter, please. Yeah, the floor is yours.
Yeah. I'm gonna move my presentation. The bar is in the way. There we are. Voila. Okay.
Great. Yeah.
And I'm going to reduce this so I won't be able to see you, but then you won't have a great big bar in the way either. Right. Okay. So so I'm representing Eurobis today. Eurobis is the European node of the Ocean Biodiversity Information System, OBIS, and we aggregate quality-controlled and interoperable data on biological occurrences and their associated measurements and other information. So occurrences, detections of organisms or non-detection of organisms, is the fundamental sort of data point in our data sets. We collect our data from organizations, projects, partners, and individual scientists as well. Here on the left, you can see a list of some of the organizations that we collect data from. At the moment, we have about almost 41 million records from over 1,300 data sets. Eurobis is the backbone database of EMONet Biology and LifeWatch. And our data are regularly harvested into OBIS, obviously, since we're the European arm of OBIS, and GBIF. Now, because our data and our metadata are harvested by others, and because our tools are written to access the data and provide them to users in different ways, it's necessary that both the metadata and the data are interoperable, and access to them is possible by machines. Now, OBIS, GBIF, and Eurobis all use the Darwin Core standard for the metadata and for the data. We all use control vocabularies within the data sets. Eurobis makes heavy use of World Register of Marine Species, marine regions, and the BODC terms. And not only do we use these terms, but we use them as URIs rather than just as strings, so that this makes them not only machine accessible, but machine understandable. For our metadata, we use the EML, the ecological markup language, metadata language standard, and the data come in the Darwin Core standard, which is a zip file of CSVs, essentially. And these CSVs are very strictly formatted. The columns have got Darwin Core names, and they're filled in particular ways, not random ways. And this makes it possible for all the downstream processes to happen. For example, quality control checks, which are run on the data before we upload them into the Eurobis database. And this is done on the formatting and the content of the data that we are accepting. And various web services that are provided by Eurobis and by EMONet Biology. So this includes APIs that allow you to access data sets or access information within the database, different types of information within the database. But also LifeWatch Belgium has various R codes that will run on Eurobis data and allow you to interrogate them in different ways. Now, for Blue Cloud 2026, we are specifically working on our datasets catalog. So this catalog is what is connected to the DDAS of Blue Cloud. And this allows for the discovery and description of and access to these Eurobis datasets. The improvements that we've been making is to add more discovery terms, instruments and parameters, for example, to the metadata, to these metadata descriptions. Adding more URIs to the metadata values. So we have these for the data sets, but we had overlooked originally the metadata. So these will be in URIs rather than strings. And in particular, we are going to be exporting our data our metadata, in the JSON LD format. So this is a linked data version of a JSON description, a JSON metadata description. And the reason we're doing this is to overcome some of the limitations are in EML with respect to the metadata you can include and the way in which you can include them and link them within themselves. And that is the end of my very short presentation. I will stop sharing my screen so I can see everybody.
Thanks a lot, Katrina.
Okay.
We have a question and answer time at the very end, but I'm also inviting you all, if you have any questions, to type them in the chat or question and answer panel, and in particular for Katrina, since she will have to leave in 30 minutes, so I invite you to anticipate any questions. There is one by Barbara Magagna, I see. So I don't know what, Barbara, if you want to openly ask a question or
yes.
Yes.
So can I ask, are you using also object properties for your metadata fields? So yeah, as EML is XML based, and you are trying to make a JSON LD now.
Yes, we're forming full triples within the JSON LD. Yes, and we're using identifiers in the proper way.
So,
for
but it's not
triple.
yet published, right? It's not.
Actually, yes. We're still working on including. We haven't got all of these. We've got instruments in there, but not parameters, or the other way around. But yes, actually, they are published. It's not very well advertised, but we do have JSON LD at this point in time. Which, if you want, you can. I can send you in an email.
Yes, thank you.
Okay.
Thanks. There is another question. Can Eurobis also add to its metadata the methods used to collect the data?
Yes, so we would like to add protocols to the metadata. The protocols are requested, they're one of the fields within the data sets. So within the data set, there is a field for protocols, which are supposed to fill in. I have to say that it's not always filled in, and it's not always filled in a kind of machine useful way. So there might be just some text or some strings, a string to say SOP number 28. But nonetheless, where there is information about protocols, the idea is to pull that out from the existing database and to put it into the metadata. And there is room in EML to do that as well as a JSON LD. Then to add for future data sets, those will be in there as well. We're always dealing with the issue of, but nobody wants to put all this stuff in their metadata because people don't want to make the effort to fill this in. But on the other hand, Eurobis data we want good data and therefore good metadata, and this is necessary for protocols. So my very long answer to that question is yes, it will happen.
Thanks. I don't see the name of the user who asked the question, but of course, I mean, feel free anyhow to reach out to us should you need any further clarification on this aspect. So thanks a lot, Katrina. And there is another one. I'll take another one, then we move on with the other speaker, and you can continue asking questions in the chat. But before we change, so Isam is asking what tools you use for metadata sharing.
The JSON LD is you get it through a URI, if that's what is meant by the question. So you type in, and there's also a feed. There will be a feed with a list of all of the data sets. The JSON LD metadata, JSON LD files that you can download will be in a list that is fed out.
Okay, good. So feel free to continue on the chat while I welcome Antonio Novellino from ETT, who will present the integration of ImageNet physics data and datasets in Blue Cloud.
Thank you so much. Good afternoon. So I'm sharing the screen. Can you confirm you can see this, the screen?
Yes, perfect.
Perfect. Okay, so as mentioned, I'm going to present some steps we're doing in ImageNet physics in order to integrate, being part of the collection and data access broker system. So just to start, ImageNet physics is one of the project of ImageNet. ImageNet is the European Marine Observation Data Network. That is a European program that is somehow federating and networking about 140 partners that are putting together their expertise and their data in order to make one single shop system for the in-situ data. It is developed in thematic assemblies. So we have a project for bathymetry, for activity, biology has just been presented, and we are in charge for physics. Physics is about in situ fair data and products on ocean physics. So we are speaking about temperature, salinity, sea level, currents, and so on. It integrates both operational data, so near real-time data, and delayed mode data, so research-based approach. And that's why we are building on top of already existing marine data infrastructure and programs. And so it's quite important to mention the tight collaboration we had since the beginning with the Copernicus in situ TAC, that is one main backbone for the operational data flow in Europe, and CDataNet network of the National Geographic data centers that are hosting the validated and delayed mode data that has already been integrated in Blue Cloud. Of course, we are working on common standards and tools and best practice in order to facilitate the data interoperability and integration. Just to give you some numbers, at the moment, you can see in the system, you can reach out by navigating Immonet Physics, more than 2,300 moorings, about 1,000 rivers, about 1,000 gliders or autonomous vehicle missions, and so on. The goal of Immonet in general is to be a single point of shop for the in-situ data, but at the same time, we are also implementing some interoperability tools in order to widening the audience and the services that we can implement. And the collaboration with Blue Cloud, for example, is quite important. This is just to show you how the central portal is working. So you go to the map viewer, then you can find in the headings of modern physics, and then by clicking on that, you can see all the platforms that are the dots, and then if you click on one dot, you have access to the data that has been collected by the platform. But how it is possible to implement such integration? Then we, of course, need to also make some distinction between some kind of data that we are hosting in modern physics. So we somehow identified these three main components. We have in-situ data, that is a data is a series of values, could be a time series, like the chart that we saw, or profile, and is sampled by one in-situ platform. But then in order to make this data available to a wider audience, we need to group them because we need to facilitate the data access. So we are making available data collection that is somehow a collection of similar data. As an example, all the CTT data is a collection, or we are grouping by specific platform, HF radar, gliders, or other kind of collection that you may find. And then we have another level. Of course, we are not speaking only of in-situ data, but also of products. And in this case, it could be a reprocessing of some data that are coming into the system, or could be a product, a graded product that has been developed by one of the institutes that are participating to modern physics. For example, the CORA, the Coriolis Ocean Dataset for Reanalysis, that is developed by Ifremer for Copernicus, is also redistributed by physics. So we can see somehow this workflow in which we integrate the in-situ data. So we are integrating all the different sources that we may have. We make some collection, and we expose this information towards the central system, but also to some key stakeholder. And Blue Cloud is one of these key stakeholders. In order to do this, what we are doing? We are applying some standards. So we are using known and controlled vocabularies, and some of these have already been mentioned in the previous presentation. So we're using CDataNet vocabularies for identifying parameters. We are also adopting the European Directory for Marine Organization in order to identify the data provider. We also encourage people to apply a DOI to validate a data set. So for example, in the case that you are not federated data site, you can always submit the data to SINOE. That is quite important for the marine, let's say, community as reference. We also encourage to apply some common formats, and SCDF is one of them, and also to apply some tools that can enable the interoperability, because in the end, a modern physics is somehow a system of systems. So it's really implementing some kind of federation. And so we encourage the adoption of tools that can enable this federation. And together with that, it's also important to apply some open license on top of the data. So just, let's say, broadcasting the recommendation from the Commission, we are encouraging to apply CC0 to metadata and CC BY to data. And then, of course, it's also important to give credits to the origin, persons that are doing the activities, so the principal investigators. I mentioned tools in order to facilitate interoperability, and in physics, we are deploying and working in order to adapt and extend the features that ERDAP is offering. ERDAP is an open source project that has been developed by NOAA, and it's quite interesting because it improves the presentation of metadata, and it's also compliant with some ISO 19115 standards. It's quite interesting because it digests different formats and offers different formats, and then is also offering both web pages in order to do some preliminary analysis of the data, but also supports RESTful web services. That is quite interesting in order to build services on top of what we are already constructing. And by the way, it's also suggested by the GOOS or CG Data Management Group. GOOS is the Global Ocean Observing System. So what we implemented by applying the concept of having collection and ERDAP together. So we are implementing collection on top of ERDAP. In order to offer this data collection, we are also making available a second dataset that is a dataset of metadata. So here you can see, for example, that for each dataset, and I took the example of river flow data. If you query on Immonet physics infrastructure, you have one dataset that is the metadata of the data, and one dataset that is really hosting the data. So if you query, if you analyze what is the content of those datasets, you have that for the metadata, you have basically the list of the stations with all the key metadata that are harmonized in terms of the controlled vocabularies that we were mentioning before, and is offering somehow also the capacity of the dataset. And then as a unique ID, you can query on, as a unique ID is the platform code that is the entry value for querying the data in the data dataset, in the data collection. And so you can see the outcome for querying for a given platform, this river platform, and the parameters, and then on top of that you can implement the charts. And this is exactly the same way we are feeding also the central portal. But while working in collaboration with Blue Cloud, we noted that this level of information was not enough, because sometimes we have some, let's say, parameters that are more a concept. So we needed to implement a new vocabulary. So in collaboration with the with the British Oceanographic Data Center, we implemented this P33 vocabularies for presenting, grouping the atomic parameters that are related to hemodynamic physics. And this is a good example, because in case of salinity, salinity can be collected, can be referred as PSU, or it can be the conductivity, or could be the sound velocity towards the water column. So in order to pull together all this information and facilitate also the discoverability of this data, we are now integrating one main data set that is a collection of all these atomic data collection, and then the different collection that, of course, may be time series or profiles. And as they have different, let's say, time feature or depth feature, we needed to split them towards two different collections. So by doing this, we are also facilitating the integration towards the central catalog. So the next integration steps, I would say, towards the full integration in Blue Cloud is to complete some of the action that we have already started. So as already mentioned, we're also working in order to make a better connection between the methodology, so the ocean best practice, and the data that we are exposing, because this is quite important to know and offer a full let's say, picture how the data has been collected, which methodology has been applied to collect the data and qualify the data itself. To include also some information about the sensor and accuracy of the sensor that is very close to the concept of ocean best practice. We need to publish also some more data collection because I mentioned a couple of them, but we're still working on some other feature parameters that can be of interest of the community of Blue Cloud and marine community in general. But in order to facilitate and enhance also the way people can query the data that are exposed by physics, we are also thinking about not only, let's say, parameters-oriented way, but also considering platforms as entity that can group parameters. So we are going to make available collection of CTDs, gliders, radars, and other features. And all of this in order to have more data in Blue Cloud, data discovery and access service, and reach more users in general, and enable more services. Thank you so much.
Thanks a lot, Antonio. And as usual, if you have questions, don't be shy. While I invite the third of the speakers that we have for this first part, who is Thierry Carval, I also invite you to have a look at the data discovery and access services available directly. You'll easily find it from the main Blue Cloud website. So, and it's open, of course, to all interested users. Okay, now we move to EuroArgo, and Thierry Carval from Ephemer will explain how they're handling with semantic artifacts in this case. So Thierry, over to you.
Yes, so let me hide the comments of the meeting. Yes, okay. So I will make this presentation about the semantic artifacts that we use in Argo or that are implemented in EuroArgo for Argo. So first, so what is Argo? Argo is an international program that is observing the ocean from the interior. So it's really in situ in the ocean with a fleet of profiling floats that are drifting in the deep ocean currents. So there is an Argo Global Data Assembly Center that is a continuously managed data set of 5 billion in situ ocean observations from 18,000 profiling floats. Among them, 4,000 are still active and remain active, are continuously remain redeployed and active. And the program started 20 years ago. So the result is a data set, a collection of 18,000 netCDF files that contain data and metadata. Argo data are a major asset for ocean and climate science. It's an important contributor to IOCCP reports. So Argo data are available with a one-click download. We are not talking about semantic here, but we are talking about the basics of the semantic. So you have a DOI that gives you access to a description of the data set. The DOI is published on DataSite. And you have a description, a license, buy license, and you have a monthly snapshot of the Argo dataset. So every month we freeze the dataset. This is a snapshot, and we deliver it by way of this DOI. And you can see that the Argo data system is managed by a huge quantity. We have more than 200 contributors here, and we also have, if you go down here, an how to cite statement. If you want to use Argo data, please use this statement. And we have a huge quantity, also a huge bibliography, thousands of publications that cite this Argo dataset. Now let's go back to the presentation. So an Argo float is something that is deployed in the deep ocean, in open ocean. then it goes by a vessel or by a sailing boat. Then it starts its life going down to 1,000 meter deep and will drift for about 10 days, And after 10 days during these 10 days, it makes measurements of environmental parameters. And after 10 days, then it will go down to 2,000 meter deep or even deeper, because now we have deep cargo that go to the bottom of the ocean. And then it comes back within a few hours. It performs a vertical profile of all the ocean interior. So the core cargo parameters are the temperature and salinity. And now we have more and more additional sensors such as oxygen, pH, chlorophyll, irradiance that are measured by the ergo floats. Then the ergo floats go to the surface, send the data within 10-20 minutes to a satellite, and then it starts again drifting to 2,000 meter to 1,000 meter deep. And the life of a float is 1, 2, 3, 4, 5 years. And so when the data is transmitted, it is received by 11 data assembly centers. So it's really an international effort, and it's coordinated with 2 global data assembly centers who manage one and only global Argo dataset. So data assembly centers are feeding the GDAC, and the scientific users or the operational centers get access to Argo data from the GDAC. And regularly, the scientists perform some delayed mode operation on each of their data files or on each of their floats to deliver a delayed mode, high quality with a much better error estimation of error on measurement. And that is the delayed mode version of the dataset that is sent back within 12 years, typically, to the data centers, and that will send it back to the global data assembly center. On the picture here, you have the 160,000 vertical profiles that have been performed by Argo floats. And in green, you have the European floats that perform, so that have been measuring ocean parameters on the global ocean from North Pole to Antarctic. So Argo and Marine Eric's commitment for fair data services. So you're Argo Eric, but also I'm talking about the marine research infrastructures such as SeaDataNet, ENSO, LifeWatch, make continuous efforts on fair principles with training and experts. And the semantic web is a significant part of this activity. So for each research infrastructure, and EuroArgo is one of them, the way forward for semantic web is organized in 4 steps. In step 1, use and publish your vocabularies with PIDs. Step 2, create an ontology for modeling the information system. Step 3, use this ontology and the research infrastructure's metadata to feed a tuple store. And then you're ready for the step 4, to implement a Spark endpoint to provide the possibility for any user to make semantic queries on the data system. So the step 1, vocabularies. So this is a priority for cross-domain and integration science. We expose our vocabularies on vocabulary servers before Blue Cloud. So Marinerics did not use vocabulary server. We used only conventional documentation. So we can say that our research infrastructure were fair for humans who could read the documentation. And now with Blue Cloud and previous efforts within projects such as AmbriFair, the research infrastructure are now fair for humans and for science cloud communities. We're talking here about machine-to-machine workflow through vocabulary server. So each of the marine research infrastructures now manage its vocabularies. And these are distinct vocabularies, but with smart mappings between, we have smart mappings between the research infrastructure vocabularies. So the marine vocabulary community activity is well managed around the NERC vocabulary server. Here you have the vocabulary server that we use in Argo, that is used in CDataNet, that is used, Antonio mentioned EmodNet also. So these are the vocabulary tables that are used by the marine community. And in blue, from R01 to RTV, you have the vocabulary tables from Argo. Let's have a look at the table R03, the physical parameter vocabulary. So all these terms are the terms, the variables name, the variable name that you will find into the collection of 80,000 Argo NetCDF floats. So let's take the term oxygen, for instance. So I click here and I have the vocabulary server provides me a URI to describe this, so a unique term to describe this concept, which is a dissolved oxygen concentration, and a definition, a unit, and so on. And as I said, a very interesting feature work that is important for interoperability is this kind of concept, same as, so the Argo doxy parameter is the same as the P01 oxygen expressed by the P01 vocabulary, which is widely used by communities like CDataNet. And so we have a description of a mapping, and this description, which is a RDF mapping statement, and this mapping statement is saying that oxygen in Argo is the same as this parameter in vocabulary called P01. And here is a description of oxygen concentration per unit mass in the BODC parameter vocabulary. And very interesting, here we see that it's the same as R03 doxy, so Argo, but it's also, as a broader term, it's equivalent to the, it's included in the A05 essential variable called oxygen. And the essential variable allows grouping of different features of and flavors of oxygen. I come back to the presentation just to mention that all this is a community work. And here is, for instance, on GitHub, the GitHub page where the Argo community is continuously working on its vocabularies. We have a lot of work to do, and we manage that into some issues. And you see that we have 9 actions in progress, and we have 36 actions that have been closed. So we agreed on this parameter and that parameter and so on. So this is a kind of description of the work we are actively doing on the step 1, which is use vocabulary. But that's why would we do that? For semantic web, this is which is a major contribution to cross-domain and integration science. So the step 2 is beyond the vocabularies, ontology are managed for research infrastructure specific domain. Then a step 3 is to have a triple store that contains the metadata described with the ontology. And a step 4 that is Sparkle endpoint to query the ontology. So we now provide semantic queries on our metadata with 7 Sparkle endpoints and more to come. So this is the example of the Argo ontology, which is described here. And this is an example of a query of this Sparkle, of this ontology. I want to have oxygen, I want to have the list of floats that perform oxygen measurements. So if we have time, I will show it, but I'm not sure we have time. So cross-domain data and metadata queries. So we have we already performed 3 successive, so yearly fair implementation profile improvements to lead that led marine research infrastructures equipped with data and metadata API, AirDAP, and Sparkle endpoint. The fair implementation profile is an evaluation of the fairness of your data services, and this was devised by the GoFair project. We developed on top of this Sparkle endpoints and AirDAP server APIs, a broker that can perform federated queries on distinct marine arrays, so the 5 marine arrays, and provide data scientists with the data corresponding to the criteria from the different research infrastructure. So this broker is available on GitHub and is flexible and to be extended to new data sources. So this is a major contribution for cross-domain and integration science. And this is a graphics that show you, this illustrates what is done within the marine arrays infrastructure. So Argo, Enzo, LifeWatch, ICOS, CDataNet have data repositories at the bottom here. The work of the Blue Cloud is to work on to make available back office machine-to-machine services, and among them you have search engine, AirDAP, Sparkle endpoint, metadata, API, vocabulary, and so on. So, and these services provide resources for marine brokers, for dashboards, for data services available on USC Marketplace. And just to finish, here is an example of a use of a Sparkle endpoint. So this is the Argo Sparkle endpoint. And I will query here, let's query in the Sparkle endpoint the list of floats that perform oxygen measurements. So this is here, I copy pasted a request that look for float whose SOSA, so SOSA is a description of sensors. So for float platforms that have a sensor that observe the term R03 doxy I mentioned earlier. So this is oxygen by Argo. So I search here, and within a few seconds, you have all the list of the floats that perform oxygen measurements. And then we are in the world of the machine-to-machine, but human can use it also. If I copy and paste one of the answers, you immediately go to the services that have, here we have an interface that query data services, and that is just showing you this particular Argo float, that is a US Argo float, that performs here oxygen measurements with this sensor. And I think I'm done.
Thanks a lot, Thierry. Really interesting and complete. We are running a little bit late in the agenda, but I would welcome a question. I see a hand raised by Denitsa Stolova. So either you type the question or I'll allow you to speak. Denitsa, do you have any question or? No, then feel free to type maybe any questions while there is another one for Barbara that I'm sure, Thierry, you can handle via the chat. So we've heard how implementing interoperability cannot be done by yourself. So that's why the second part of the agenda welcomes speakers that represent initiatives beyond Blue Cloud who are developing services and methodologies for machine-to-machine semantic interoperability. And the first on the list is Fernando Aguilar Gomez from CSIC, the Spanish National Research Council, who will present FAIR EVA.
Good. Yeah, give me share my screen. Okay, I hope you can see my screen now.
Yes.
Okay. So good afternoon, everyone. I am Fernando Aguilar, and I'm going to present FAIR EVA. That is one of the tools for fair assessment that we develop under the context of EOSC Synergy project. So Well, I guess since you are here, you already know about the FAIR principles. They are a kind of high-level perspective, but what we wanted to do with FAIR is moving from principles to indicators. And to do that, we adopt the list of indicators developed under the context of the Research Data Alliance and the FAIR Maturity Working Group that list around 40 indicators that wanted to provide more details on the FAIR principles and sub-principles. So the goal and the challenge here was to implement at technical level and in an automatic way those indicators that potentially be adapted to different domains, even for generic repositories, since we started with our institutional repository for data, Digital TSIC. So, FAIR-EVA means evaluator, validator, and advisor. And we want not only to evaluate the level of fairness of data and other digital objects, but also validate the status. And what is more important, I think, in this context, is to advise how this level can be improved. And to do so, being compliant with the FAIR data principles, the kind of things that we need to check and to assess is, for example, the data within the context of a multidisciplinary repository, but also taking into account that different disciplines implies different data formats, for example. And we also wanted to make it flexible enough to create or to add new custom tests, because, for example, for data, any disciplines wants to check different things sometimes. Also, to check the metadata, if, for example, if it is adopted community standards and if it is machine actionable, like those examples that we have seen before. To check also the fairness level, we need to check if the metadata is identified with a persistent identifier, for example, DOAs, etc., and if they are provided by an accepted authority. And finally, to provide some examples, the repository or the data service need to provide indexing features to make the digital objects and data machine actionable. Well, the challenge also for FAIR-EVA was that we wanted to adapt the tool to different domains, starting from Digital TSIC, that is a multidisciplinary repository, but also taking into account that different data services or repositories means in some cases different metadata standards, different technology behind. So the idea in this case was to start the technical implementation, starting from the Research Data Alliance list of indicators, but providing an architecture that allows to adopt any other list of indicators and be flexible finally. Not only flexible, but also modular and scalable. That means that, well, for big repositories with millions of records, we need to create an architecture capable of assessing a big number of digital objects. We started also with a generic implementation using the OIPMH protocol. That is one of the protocols that most of the data repositories adopt, but having in mind this system of plugins that allows the integration with any type of data portal. And one of the interesting features is that we wanted not only to evaluate the fairness level, but also validate, and what is more important, advise the data producers, for example, how they can improve this fairness on their data or digital objects. So that The target of this tool is mainly data producers, but also repository and data portal administrators in order to allow them to know which features they need to implement on their service. And finally, funders to check, for example, if a set of data within a project is fair enough or not. At a more technical level, the tool is implemented in Python, and this has those two I mean, for one hand, we have the web interface that connects with an API that is scalable, and we can make the test with that. If you want to know more on how it works, this YouTube video with a demo. To provide a couple of samples on the technical implementation, for example, for one of the indicators of the RDA, regarding findability, that means metadata is identified by a persistent identifier. What we do at technical level is to search within a predefined list of potential metadata terms, for example, identifier, and we check if this information is available on the metadata. We check if it is okay, etc. Also, for example, for accessibility, we want to check if the metadata can be accessed using a standardized protocol, and we are doing it automatically. For example, checking the way of accessing to the metadata, if it's on, for example, OIPMH, if it is through an API, etc. For interoperability, we have a list of control vocabularies, and we check in specific metadata terms if they adopt this control vocabulary. For example, the geonames, ORCID also for indicating contributors on the digital object, etc. And more specific tests about, for example, attributes in the metadata, etc. This is more or less the architecture. As I said, we have a front end that is a web interface that connects with an API that is basically the Feriba engine that performs all the required tests. And in order to make those tests, we need to access both data and metadata. To do so, we have different plugins. The one generic with OIPMH, we have the plugin for our repository data.test, but we are developing some different plugins to connect, for example, to the data systems from different EOSC-related projects like EOSC Siesta or EA4EOSC. We are developing also a plugin for GBIF in Spain, also extending the RDA indicators to perform more tests based on data. For digital twins, we are also developing a plugin for DTGeo project. And regarding marine sciences, we are also collaborating with Imagine project to check the data for that project. This is how the web interface looks like. The idea is to provide a persistent identifier, for example, a DOI, and the test is run on a specific plugin, and you will obtain a set of score for all the fair indicators. If you extend the list of findable, accessible, etc., you will find more information about each of the tests, and you will get information and tips about how you can improve that specific indicator. For example, it can suggest you to add more metadata terms or more specific, to use some particular control vocabularies and that kind of things. And more related to marine, as I said, we are working on a potential Imagine project plugin. The idea of Imagine is to publish the data on Zenodo and adding more metadata, for example, in XML. And we are developing a plugin to access to Zenodo, to the Imagine collection, and adopt the list of tests to get that customized metadata and check all the tests with that metadata. The thing is that in different disciplines, we are using different metadata standards, we are using different formats, and in some cases, it is very difficult to have a generic tool. So our idea is more allowing to the disciplines to adopt the test to their specific cases. That's better for them because they can adjust, for example, how a particular test is done on the context of their discipline or the community, and it's more flexible finally, and they can do more concrete things. And that's all. You have any questions?
Thanks a lot, Fernando. I don't see immediate questions in the chat while I see some activity in the chat. So for now, I thank you, and I invite the next speaker on the floor, Barbara Magagna from the Go Fair Foundation, and she will talk about Fair Connect.
So can you hear me, hopefully?
Yeah,
And
perfect.
see the screen.
Yes.
Thank you for inviting me to present about Fair Connect, which is a new component showing results from the FAIR implementation profiles that were mentioned a few times today. So outside the data stewardship wizard, we can now also find better results about the choices taken by a community in a platform. Yeah. So this is how it looks like now. And this is an initiative from Go Fair Foundation, CoData, and iOS Press. And actually, it will be improved in the next 10 days. So by end of April, it will be much more easy to use it. But actually, Fair Connect is an open access publishing platform for good practices for professional fair data stewardship. So in more concretely, on Fair Connect, you get information about resources used to support fair implementation. We call them these resources fair supporting resources, and they are displayed and findable on Fair Connect for humans in form of articles, journal articles in the Fair Connect journal, and for machines. And these are then expressed as nano-publications and that provide identifiers for each of the resources and metadata about these resources. And you can find them in the search engine. So the HTTP will be replaced by end of the month with HTTPS, and it will be much more performant. We use, as I said, we call these resources fair supporting resources. They can be of different types. And initially, the people from ENRI knew this as fair enabling resources, and we call this as a subset of these fair supporting resources, those resources that are essential for implementing the FAIR principles as enabling, and those that are supportive as supporting. And here you see the FAIR enabling resources to address each of the FAIR principles, like identifier services, metadata schemas, structured vocabularies, data usage licenses. The idea is that we want to collect these resources and make those available to others, also to inform communities that have not done already this FAIR roadmap, not started the FAIR roadmap, can learn from other communities which resources they used. And as said, these are expressed as nano-publications, and you see here, for example, OGC sensor ML as a resource, a fan-enabling resource that is of multiple types. It is a metadata schema, it's a semantic model, and it includes also provenance modeling. And you can see this as a machine-readable resource in Fair Connect, in NanoDash, but also in the FIP wizard. And what you also can see that we reuse existing descriptions if available from fair sharing. And you see this in the provenance part of the nano publication. And you can also see here that same as is used here also for the mapping between the resource here and fair sharing. Another example are the NERC vocabularies that I also mentioned already. These are described as fair enabling resources for structured vocabularies. And here also we make a reference to fair sharing. In addition, you can collect all these fair enabling resources in a profile called the Fair Implementation Profile. And you see here the ontology, the FIP ontology that explains that a community can make FIP declarations about the use of a fair enabling resource for a specific FAIR principles. And this list of FIP declarations are collected together as a nano publication index. And in addition to the FIP, we have now also the semantic interoperability profile that has been developed for the EOSC Semantic Interoperability Task Force. And what we wanted to have is there a survey or a possibility to ask communities which resources are they using to achieve semantic interoperability. So we were looking for FAIR specifications like metadata schemas, ontologies, etc., but also crosswalks, which are FAIR mappings. Apart from the specifications, we also wanted to understand which services they are using for actually creating a semantic artifact, for registering these data or metadata or validating them. And also we were looking for FAIR practices that can connect different methods and specifications in one resource. Fair Connect allows to find all these resources, so the FAIR supporting resources, they will be filterable by type. So you can then really search specifically for vocabularies. You can also find out how many communities are reusing the same resource. You can also find out if this description has been qualified. We have a qualification pipeline in the background for making sure that these descriptions are valid and useful. And then what you can also find are FAIR implementation profiles with the associated FAIR supporting resources and the semantic interoperability profiles with the FAIR supporting resources. And this is independently where these resources have been developed or generated. And the last now is that we also have a dashboard where you can see this in a graphical way. So FAIR supporting resources by types. Soon also clickable to see all FAIR supporting resource instances per type, the FAIR implementation profiles, and the semantic interoperability profiles. So thank you very much for your interest.
Thanks a lot, Barbara. Nice to see these tools available for the community. Now we move on, we go back to a specific, let's say, earth science case. So I invite Guillaume Alvizet from DataTerra, and he will explain how they're setting up the Earth portal on the ontology and vocabulary repository for the earth sciences, which has also connections with the data that we handle in Blue Cloud. So Guillaume.
Thank you, Sarah. I will share the screen. All right, so hello everyone. My name is Guillaume Elvisé, and I'm an engineer working at Datazera, research infrastructure for the R system and the environment. And I'm going to present the work I did with Christian Pierco about the ERS portal, which is a semantic artifact catalog for the R system. So to give a little bit of context, ER sciences in general regroup a lot of communities. So there are a lot of semantic artifacts. So by semantic artifacts, we're using here the Ferris Fair definition, which regroups vocabularies, ontologies, thesauri, etc. So I'll be using that term from now on. So we have semantic artifacts well everywhere, spread across the different communities, and the different communities doesn't especially communicate with each other on how to do stuff or what to set up. So we often have some discrepancy when it comes to do some pluridisciplinary work. So we want to unite we want to unite the artifact from different communities. We can have some issues like about discoverability. We can have some issues about things that are not always the same. So in this context, we set up the Asperol, which is financed by the Fair Impact project. And we try to find a common ground between all the our science communities and provide tools for them to work with their semantic artifacts if they want to work with other communities or for their own community as well. The Asperol is powered by the interoperable technology. So it has a lot of different features, so it can accept like all different kinds of representation language of the semantic web, namely OWLs, COS, RDFS, etc. So we can accept like ontologies, vocabularies, all kind of complexities. There's a versioning feature which can track all the different version of your vocabulary. We can also track and add some mappings on between the different semantic artifacts. We also have a tool called the annotator, which allows you to basically propose some annotation if you provide a text or keywords as an input. We also have a recommender, which can recommend you an ontology of a vocabulary depending on your text as well. And for the developers, we also propose an API from which they can access the entire content of the ERS portal. And we also provide another service, which is about the fairness assessment of the semantic artifacts. I'll say a little word on the Ontoportal Alliance. So the Ontoportal technology is also deployed on other communities as well. So like historically speaking, the first one was BioPortal, but then we've seen several community getting interested into the technology and deploying it. So there is AgroPortal for the agri-food community, there's EcoPortal for ecology and biodiversity, etc., etc. And the advantage of the alliance is that we share the same code, the same code base, so we can benefit the feature of each other, some fixes as well, and we also try to move forward, generally speaking, as a group. So, namely for stuff about federation, for example. So the ERS portal is a catalog of semantic artifacts. So you can browse the different available semantic artifacts with and filter them by category or groups. So for example, here I took the oceans semantic artifacts. You can also browse and the different ways. Like for example, if you want to, if you have an abstract from a paper, you can also see what could be the corresponding semantic artifact by using the annotator or the recommender. Here I took the example of Argo because conveniently Argo is also present in the Ars portal. So we have when you go to the page of an entry, you got all the associated metadata, and we vividly encourage to add more metadata if possible. A semantic artifact like a vocabulary and an ontology can be fetched from another repository, which is not kind of problem. We don't force people to monitor the stuff directly on the Ars portal. So we can update vocabularies and ontologies from the source directly. And on the details, we can browse directly, of course, the content of the vocabulary. So here, for example, you can browse each different table of Argo, and the entire metadata for each semantic artifact is displayed there. We also have some other tabs at the top. The most interesting ones could be the mapping ones. Since when you upload something in the Ars portal, it will automatically detect if there's some overlap in terms of lexically. Well, if some terms are lexically identical to some other terms that are already present, it will automatically do that. And if you also have some mapping relation that you've included in your vocabulary, it will also display there and display all other vocabularies to which it is mapped on the Ars portal. And we plan to extend this feature in the future. So I will expand much more on the other tabs, but we just for information, we'll also have a notes tab, which acts similarly to GitHub issues, which can be pretty useful to have feedback on your vocabulary, or like if developers or like the editors of the vocabulary want to discuss between them. This is a useful feature. And when I say what about the fairness assessment tool, which is called OFAIR. The way it works is that it takes the metadata of a vocabulary that is in the portal. So it will take not actually the metadata from the content of the vocabulary, but rather the metadata of the entry of the portal itself. So in the 15 FAIR principle, there are 61 questions total, which are specific to semantic artifacts, which is not always the case for other tools. With this tool, you can also compute the score of a single or several entries of the portal. And there is the assessment grid is based on the following publication that is on the screen. Well, all detailed information can be found on the GitHub repository of this tool. And I just want to provide a little bit of example, because this tool gives actually like a working ground for if someone wants to increase the fairness of the semantic artifact. The score itself does not mean you're necessarily good or bad, but it gives you an idea of what you could possibly improve. So there are still some questions that we cannot resolve. So the score of some questions or some FAIR principle will be low, of course, because we cannot evaluate some questions. And some some questions are not always relevant depending on the situation. So it's more giving a tool, more giving something to work on to see what you could improve rather than a definite way of evaluating your semantic artifact. So there are several fairness assessment tools out there depending on what you're looking for, and each tool provides basically a point of view of what could be improved. And this is the case here. So yeah, I think that's mostly it about Allfair. So the RS portal is also currently used in different projects. So for example, there is the semantic analyzer in Fair Ease project that is a source. So basically, the semantic analyzer uses the RS portal to fetch the content. And a second use case is the keyword annotation for Easy Data. So Easy Data is a French repository for long trail data sets. And basically, we're currently working on providing the keywords based on the abstract of the dataset when you want to send. So you will have suggestions from the annotator of the RS portal when you submit an abstract. So that will enrich the total amount of keywords you can have. And especially, for example, if there's a keyword that maybe not exist in the current system, well, with the RS portal, you will certainly have more keywords available. So thank you for hearing me. If you have, I don't know if there are some questions.
Thanks a lot. Thanks.
I see Barbara actually asking questions. So I can give you my email if you want to know more about this this particular matter. For anyone else, if you have any other questions, you can of course send an email at the address shown at the bottom. Thank you.
Thanks, Guillaume. And so it's nice to see that you took Argo as a case, and since we started with Thierry by explaining Euro-Argo semantic artifacts within the Blue Cloud framework, now we call back Thierry on stage to conclude with the last speech that will highlight a little bit about the insights from Eurogoose, so another huge network that we have in Europe, which is also contribute to the overall Blue Cloud dissemination, and in particularly about some recent insights from Eurogoose data management practices. Thierry?
Yeah. So
Yeah.
should I start?
Yeah.
Okay, so I have minus 10 minutes to make this presentation. So insights from Eurogoose data management practices. Next. Sorry. So what is Eurogoose? Eurogoose is a European Global Ocean Observing System. Eurogoose is composed of 44 member organizations that are part of this association from 18 countries, and 130,000 organizations are involved in the Eurogoose activities, not necessarily as member, but as member or as part of the regional operational systems, working group or task teams. So this represents 30 countries. So the vision of Eurogoose is sustained ocean observing and operational oceanography services that benefit the European society and that are supported by the European society. The mission of Eurogoose is to lead the development and the implementation of sustained and coordinated operational oceanography across Europe. So Eurogoose is organized in working groups, task teams, and regional systems. So in the working groups, we have 6 working groups: biology, coastal, data exchange, come back later on that, ocean literacy, science advisory, and technological planning. We also have task team on particular platforms of observation. One of these task team is Argo floats. The other one is ferry box, fixed platforms, gliders, HF radar, tide gauzes. And the very important part of Eurogoose are the regional ocean observing system. So there are 5 regional ocean observing systems: Arctic, Baltic, Ireland, Biscay, Iberia, NUS, so the Northwest Shelf, and the Mediterranean system. So data exchange, it's the working group we are 30 experts in European data services, European and international initiatives, involved also working with the Eurogoose regional systems and task teams. So a recent work of Eurogoose was the adoption by all the members of Eurogoose, so the 44 members, of a data policy, the Eurogoose data policy. So the Eurogoose data policy is the European implementation of the International Oceanographic Committee data policy, IOC. So it states that core marine data should be shared with minimum possible delay. So all our institutions signed to that. We say that core data, at least physical and BGC, biogeochemical essential ocean variables of the global ocean observing system, should circulate freely, should be shared. Free and fair access circulation of EOV data. So this should be shared through open and free license. And we recommend using the CC BY license. Available with minimal restriction on use, unless there are valid reasons to restrict the access. So it should be consistent with national jurisdictions, international conventions, treaties where applicable. But the default is it should be able to circulate. Quality controlled and accompanied with metadata. Sending raw data on internet is not enough. We have to provide quality control data with metadata accessible through a web interface and machine-to-machine protocols. So data in the end, should be submitted to European and international open data systems and engage Eurogoose members, organizations, and community to commit to this implementation. So Eurogoose data policy is a European implementation of the IOC data policy. It is our commitment for ocean data circulation and use in support of European and global policies and societal challenges. This data policy promotes ethically open data, as open as possible, as close as necessary, clear and ambiguous data licenses such as CC BY, so that you can reuse without any fair the data you did get from these European data services. Long-term archives in certified repositories and fair principles, and such as persistent and globally unique identifiers, PIDs, for better data citation and credit to providers. So where are we now? So the Eurogoose data policy is now an ocean best practice publication. It is the latest release of Eurogoose community best practice in the ocean best practice publications. And you can see here the page of ocean best practice with the Eurogoose community documentation. And the last one is the most recent one is the Eurogoose data policy. And but we regularly publish papers on, for instance, ocean literacy, Jericho implementation, ferry box white book, and so on. Sorry. So I want to mention here also that a typical activity of Eurogoose is coordination. So an European coordination for Eurogoose, Copernicus Marine Service Institute DAC, Emonet Physics, Chemistry, Ingestion is something important. So how do we work together? So through Marine Institute Collaboration Working Group. This is the MIC working group. The practical objective of the MIC working group is that if some one of us reach one provider, when one of us contacts a producer, the effort will benefit from it. So this will avoid confusion on providers. Should I make available my data to Eurogoose, to Copernicus Marine Service, to Emonet Physics, Chemistry, Ingestion? We coordinate the activity and answer this question within the MIC working group. So what next in Eurogoose? So what are our important topics that still need to be addressed? So data policy is a commitment for fair data, but that's not enough. It means that we have to continue efforts to improve citation and credits to data providers through DOI best practices and CDataNet vocabulary such as EDMO codes to identify the institution from where the data is originating. And I should also mention ORCIDs, to identify scientists that provided efforts on datasets. Synergies with Eurogoose ROSIS working group and task teams. So as an example, we are contributing to the Ocean Glider NetCDF format implementation, which is an international activity organized by OceanOps at global level, HF Radar NetCDF format improvement with global attributes, compression, Copernicus and CDataNet joint data format, BGC synthetic profiles toward Copernicus Marine Institute NetCDF, one format for core Argo and BGC Argo data, CDataNet NetCDF and vocabularies for ship ADCP. So this is part of the Eurogo ship project. And we are also very active, and we know that there is a lot to be addressed on cloud native data assembly centers, data centers workflows on DAC, in a cloud infrastructure, such as, of course, the Blue Cloud. And that's all I've present about Eurogoose. This was a brief highlight.
Thanks a lot, Thierry. Thanks all the speakers, and thank you all for joining. We hope that you received useful information. We're approaching the end, but before we leave, I want to mention that we are building a training catalog of materials that will be available via the website on Zenodo and via dedicated catalog. It's already there, but we are increasing the number of materials that are available from Blue Cloud, but of course referrals to the resources that we are also relying to from other initiatives will be part of the offer. In addition, starting from autumn 2024, Blue Cloud will launch a proper series of courses, so a few courses delivered via and in collaboration with the Ocean Teacher Global Academy of the UNESCO, so in collaboration with the OBVS team, to explain how to use, exploit, and make best of use of the Blue Cloud services and products. And if you haven't done so, there are a few channels you can use to follow us and get insights of when all this will be delivered. And last but not least, we have a call for papers open in collaboration with the International Journal of Data Science and Analytics. So we invite you all to have a look and think of applying and submit a paper. The deadline is the 30th of June, and it's open to any research teams and actors working with blue data and, let's say, open science in relations to the blue economy and marine science. And we leave you now just by asking you what have you learned from today. So very last small request for those who are still with us. If you want to go back to the Menti and leave us a message on the main insights, a word, something that you've retained, something that you think will be useful for your work after this webinar, that would be very useful for us to progress on the work that we are doing to ensure dissemination of fair data practices in the marine research domain. So before leaving, leave us your words. And with that, I also take once more the opportunity to thank all our speakers for being with us today and all of you for joining. Thanks a lot, and stay tuned with the next series of webinars.
Thank you, Sarah.
Thank you,
Goodbye.
Sarah.
Bye.
Bye-bye.
Thank you,
Thank
Sarah.
you.
Bye.
Bye bye.
Bye.